A team spends 8 weeks building a language model for an internal document search. They pick a model, write a retrieval layer, wire up a basic interface, and ship it. Users are happy for about 3 weeks. Then the complaints start. Answers that were accurate are now wrong. Documents added 2 weeks ago are not showing up. Nobody can tell which version of the model is running. When a response is confidently incorrect, there is no way to trace why. The model still works. The stack does not exist. The team built one layer of a 7-layer system and called it done. This article is the blueprint they did not have. This is the LLM stack in plain language. Models part 4. 7 layers. Each one has a job. Miss one and you'll find out the hard way. Section 1. The stack before the tools. Every article in this arc references layers by name: data pipelines, embedding models, vector stores, model registries, inference servers, monitoring. Those references only make sense if you know where each layer sits relative to the others and what job it is doing. The stack is not a preference. It is a sequence. A language model without a data pipeline has nothing to reason over. A retrieval layer without an embedding model cannot find anything. A deployment model without monitoring runs blind until users tell you it's broken. Skipping layers does not simplify the system. It moves the failure somewhere else harder to find. This article makes the sequence explicit. The tools come later. The sequence comes first. Section 2. Parameters. What are they? Before mapping the stack, one term needs to be precise because it appears in every layer discussion that follows. Parameters are the numerical value a model learns during training. Every connection in the neural network has a weight, a number that gets adjusted millions of times during training until the model produces useful output. A 7 billion parameter model has 7 billion of these numbers. A 70 billion parameter has 10 times as many. More parameters generally means more capability and more memory required to run the model. A 7 billion parameter model quantized to a 4-bit precision fits in 4 gigabytes of GPU memory. A 70 billion parameter model at the same precision needs roughly 40 gigabytes. Parameter count is not the only measure of a model's capability. Newer architectures extract more from fewer parameters, but it is the first number you need to understand when evaluating whether a model fits your hardware and your use case. Section 3. The 7 layers. First, the data layer is where everything begins. Raw text arrives from documents, databases, APIs, logs, and external feeds. For this arc, that means NOAA storm event records, structured data with event dates, locations, and severity classifications alongside free text narrative descriptions of what actually happened on the ground. The data layer ingests, cleans, and stores this material, informs the layers above it can consume reliably. Nothing above this layer works correctly if this layer is producing garbage. Second, the embedding layer transforms raw data into numbers that capture meaning. An embedding model reads a sentence and produces a vector, a list of numbers, that represents where that sentence sits in a high-dimensional space of meaning. Sentences with similar meanings produce vectors that are close together in that space. This is what makes semantic search possible. When a user asks a question, the embedding model converts the question into a vector, and the system finds text chunks whose vectors are nearest to it. The quality of your embedding model determines the quality of your retrieval before the language model ever sees a query. Third, the vector store layer holds the embedding produced by the embedding layer and makes them searchable at inference time. This is a database optimized for one specific operation. Given a query vector, find the stored vectors most similar to it as fast as possible. Pinecone, Weaviate, and Chroma are the tools most commonly used here. The vector store is what gives the language model access to your data rather than just its training knowledge. Fourth, the model layer is where most practitioners start and where most of the visible tooling lives. The language model itself, the weights downloaded from Hugging Face or a commercial provider, lives here. It receives a prompt assembled from the query, and the retrieved context generates a response token by token and returns it to the application layer. The model layer depends on every layer beneath it. The model served without a retrieval layer can only reason over its training data. A model served without clean ingestion data has nothing to retrieve. Fifth, the serving layer takes the model and makes it accessible as an endpoint that applications can query. This layer manages how inference requests are received, how the model processes them, and how responses are returned. It handles concurrency, meaning multiple users querying at the same time, and manages the hardware resources the model runs on. OLLAMA and VLLM are the tools most commonly used here. Without a serving layer, the model runs as a script you execute manually. With one, it runs as a service. Sixth, the orchestration layer assembles the pieces the model needs to answer a question. When a query arrives, something has to retrieve the relevant context from a vector store, format it into a prompt the model can use, send that prompt to the serving layer, and return the response to the user. That something is the orchestration layer. LangChain and Llama Index are the tools most commonly used here. This layer is where RAG, Retrieval Augmented Generation, actually lives in practice. The concept belongs to the architecture. The implementation belongs here. Seventh, the monitoring layer watches everything above it and below it continuously. It tracks whether responses are accurate, whether the data feeding the system has shifted from what the model was tuned on, and whether the infrastructure is serving requests reliably. Without this layer, the stack operates blind. Problems accumulate invisibly until users report them rather than the system detects them. Section 4. Open weight versus open source. This ARC uses the term open weight consistently, and it is worth being precise about why. Open source software means the source code is available, modifiable, and redistributable under a license that permits those things. Open weight models make the trained weights available for download, but the licenses governing what you can do with them vary significantly. Some permit commercial use without restriction. Some require attribution. Some prohibit use above a certain revenue threshold. Some restrict fine-tuning for specific purposes. When someone calls a model open source, they usually mean the weights are publicly downloadable. That is not the same thing legally or operationally. Before you build a production system on a model, read the license. Llama 3 has a custom meta license with commercial use provisions. Mistral models use Apache 2.0, which is permissive. Gemma has a terms of service that restricts certain use cases. The capability difference between these models matter, so do the licensing differences. Section 5. Dense model versus mixture of experts. Two architectural terms appear throughout the model landscape discussed in Part 2 and deserve a precise definition before the build article uses them. A dense model activates all its parameters for every inference call. Every one of those 7 billion or 13 billion weights participates in producing every response. Dense models are straightforward to serve and their memory requirements are predictable. A mixture of experts model divides its parameters into specialized groups called experts and activates only a subset of them for any given input. Mixtral 8x7b has roughly 47 billion total parameters, but activates only about 13 billion for each token it generates. The result is a model that performs like a much larger dense model while consuming memory and compute closer to a smaller one. The trade-off is that mixture of experts model are more complex to serve and can behave less predictably when the routing between experts does not match the domain of your data. For a first build, a dense model is the right choice. The behavior is more predictable and the serving infrastructure is simpler. Mixture of experts becomes worth evaluating when you have the first system running and you're optimizing for capability per compute dollar. Section 6. How the layers connect. Data flows up, failures propagate in both directions. A document that enters the data layer with encoding errors produces a malformed embedding in the embedding layer, which lands in the wrong neighborhood of a vector store, which gets retrieved in response to queries it does not actually answer, which causes the model to produce confidently wrong responses, which monitoring detects weeks later when user complaints accumulate. The failure originated at layer 1 and surfaced at layer 7. Without instrumentation at every layer, tracing it back requires investigation rather than observation. The propagation logic is what separates practitioners who debug production systems in hours from those who spend weeks chasing symptoms. The stack is not 7 independent components. It is one system where every layer's output is the next layer's input. Section 7. What comes next? The next 2 articles deal with the data, the foundation the rest of the stack depends on. First, why your data is probably not ready for a language model pipeline, even if it was ready for everything else you have built. then how to get it in. The NOAA Storm Event Dataset threads through both. It has the right combination of structured metadata and unstructured narrative text to make every data preparation decision concrete rather than theoretical. The stack is the blueprint. The next article is the foundation.